Okay, welcome everybody. Thanks for making it to the first session of the day. So first, hands up here, who's heard of RTPProxy before? Okay, pretty good. Yeah. Who's actually used RTPProxy at some point? Ah, very good. Who actively uses RTPProxy? Pretty good. Okay. So I'm Max.
I'm Jev.
And yeah, we're from CitySoft. I'll keep this really quick. So CitySoft, we're a Canadian company. We have staff in the Ukraine, Australia, and Canada. We make soft switches, and above all, we love networking, computers, open source, voice over IP. So what's RTPProxy? It's a network proxy generally for video and voice, but I'm speaking at OpenSIPs Summit, so you guys know this. Bit about the backstory. So the first use case for RTPProxy was network address translation. Originally, some of the early SIP user agents, they didn't know things like stun or ice or turn, so they couldn't deal with network firewalls, network address translation firewalls. So Max started out by writing the NAT helper module for SEN's SIP Express router at the time, and that took care of the SIP protocol side of things, but it didn't address the media side. So that's when, in early 2000, Max started on RTPProxy, which allowed RTP to traverse media, which at the time was pretty novel, and it worked out pretty good. But NAT wasn't the only use case for it. After that, the next use case that was sort of realized was network topology masking, which is sensible. Operators typically don't want their customers to know who their vendors are. They don't want their vendors poaching their customers. And also it's useful, in anyone who's dealing with networking, it's nice to define an edge to your network. And also some astute vendors will also get you to whitelist your media endpoints as well as your SIP endpoints. A lot of don'ts. They just say, oh, give me your SIP IP, we'll take media from everywhere. But not any of you guys. You guys know what's going on and know how to secure networks. And there's also, so another use case that we run into regularly is regulated industries. So banks, for example, they're regulated by the SEC and FINRA to record certain voice calls. They've been doing that for email for years, but it's been happening in the voice domain now as well. You also have things like CALIA in the US, Acts 1979 in Australia, RIPA in the UK. These are all lawful intercept acts for various territories, and it varies by territory to territory. You can only do this, again, if the media traverses your network. And then, I mentioned as well about defining an edge. Operators want to know what's going on with their voice traffic. You want to be able to track metrics like voice quality, packet loss, jitter. You want to be able to catch problems early and proactively. You can only do this if the packets are traversing your network, and you can do that with RTPProxy.
Okay, so a little bit of technical side. Some of the design consideration, design objectives that we apply when working on the RTPProxy. First, we wanted something that runs completely in userland. The reason for that is basically security, and we wanted to be running 24/7 pretty much. We wanted it to be fairly simple. We did not want to have one tool that does it all, like say Asterisk or something. So we wanted simple thing that does this forwarding and does it very well. So that was more main objectives design RTPProxy, and also wanted it to be very portable, so it can run on all modern Unix derivatives and the likes. So yeah, that's what we wanted from it. Then we started thinking about how to implement it, and one of the obvious ideas was to integrate it inside the SIP Express router as one of the modules. But we decided against that because it will again complicate the SIP Express router OpenSIPs today, and it doesn't really have any business handling media. So we wanted to have basically another process running on the same host or on a separate host. So we needed some kind of control protocol to go with it. There are few alternatives that we considered, such as MGCP, for example, but at the time we did not see any benefit of using anything that complicated. So we basically started working our own protocol, and we want to be simple, so we basically text-based, and we keep it simple so it can be pretty much easily understood by just a human being without much trouble.
Yeah, as Max is saying, so with RTPProxy, we've always focused on doing one thing very specifically and doing it well. Taking the control channel that controls RTPProxy that Max was mentioning, it's clear text. It's super simple. It has no security, and it's expected that you guys do that yourselves. We could have put on, SSL and a bunch of other stuff, but it's we leave that up to the implementers. You guys might be running this in a private network with a management network, so you won't need that stuff. Or if you're doing it over long haul, we expect that you will be implementing VPNs or some sort of tunneling, firewalls. So it's bring your own security. And the value we see there is that we're giving you a simple product that's composable. You can use in different ways, and I think that's played out. It's the RTPProxy is used in a lot of the different areas, embedded to large scale VoIP operators. It's sort of the Unix way. So composability is really important for us, and if you want it to be composable, ideally it should be as simple as possible.
Okay, so some of the history of versions of the RTPProxy that we have at this moment. First version was pretty simple. As I said, we started very lean, and the objective was to get something that works well. Also, at the time, it was pretty much single core. You rarely see dual core, not definitely on the laptops or anything like that. So we basically wanted to have good single core performance from the start, and that basically just defined some of the original design decisions. We basically worked on all of the protocol and make it working with all net scenarios. We also had support for the IPv6 pretty much from the very early days, and it's still there. So if you need any IPv6 support or any project that involves time and gateway between.
A quick question: Does anybody here see IPv6 in production? Yeah, 2, 3. That's good. Cool. We want to see more of it. We didn't believe it was happening, so at least we're seeing some people.
Oh yeah. So as I said, it was pretty simple, but it worked. But as time evolved, our needs have evolved as well as hardware that we wanted to run on. So with the version 2, we did a little bit of re-architecture in the RTPProxy, so it can support multi-threading, and basically we split up some of the processing into different threads. It's not this work is not complete yet, but it allows us to scale to pretty much today hardware, maybe a little bit yesterday's, but anyway, we're working on it. Then we added some of the new features into version 2, which includes, for example, ability to analyze RTP packets, RTP flows on the fly, so you can have usable statistics out of RTP proxy node, not just forwarding packets, which becomes pretty important as we scale it up. And then we have different statistics counters, which again allows you to track things like average session duration, packet loss, and such. And as Jeff said, we're also working on version 2, which will include some of the better multi-threading, so hopefully we'll be able to scale to bigger hardware.
So on the left side there, that's actually delivered and implemented in today's code. There's more coming. Yeah, so there's also a couple of utilities bundled with RTPproxy that most people don't know about. Make announce allows you to pre-encode audio into all popular codecs, which is very efficient. It just injects the pre-encoded audio directly into the audio stream. This is useful. You can replace comfort ringback. You can do announcements to the callers. You know, this call is going to be recorded for QA purposes, or music on hold. There's also another utility called extract audio, which decodes captured audio streams. So RTPproxy has a command, which is R in the command protocol, which allows you to flag a stream to be recorded to disk. And that stream can be decoded back to a WAV file with the extract audio utility. Extract audio as well, it's not specific to RTPproxy. You can use it to decode PCAP files from TCP dump, which is useful. It's not the prettiest utility. We probably are going to do a bit of housekeeping on it, but it's there and it exists. So if you have that use case, if you need to decode some audio, it's worth having a look at on your GitHub.
So does it have sort of pluggable payload or codec formats for the extract audio, or is it PCMU?
We support right now 729, 711, GSM, 722. Maybe something else.
But it's built into the tool rather than...
Yeah, it is at this time, yeah.
Yeah. It's basically built with RTPproxy, so as long as you have some of the dependencies, it will detect it.
Yeah.
Can it hook into an existing call, or does it have to start the call?
For the recording?
Yeah.
Yeah, you can do it on the fly. Yeah, it doesn't need to be at the start. You can do it anytime.
In the converts, you can start it and stop it.
Yes. I'm not actually sure about if you can really stop it, but I'm pretty sure you can start it anytime.
You can stop it.
You can stop it. Okay.
We need customers for it all.
Okay.
If you have that use case and it doesn't work, open a ticket on our GitHub tracker, and it wouldn't be too hard to do. And same for codecs as well. If there's some you're looking for. Yeah. Okay. So you can open a ticket and pray, buy some beer.
So can you also make announce what does it take the input WAV file or
WAV file, yeah.
I think right now it takes signet linear, but you can basically get signet linear out of any WAV file. It might take 5 minutes.
Okay.
But
it's actually
pretty easy to figure out. Yes.
Yeah.
It's also part of the test suite, so you can actually go in and see how we use it. So actually pretty easy.
Yeah. Which is a segue. So we put a bit of extra work into the testing and R&D side for RTPproxy in the past couple of years. So we have continuous integration running on Travis, which gives us builds that runs our test suite and passes packets through RTPproxy in various ways, captures them from the actual network interface to see is there any loss or anything like that. We also have an internal Jenkins system that does builds on FreeBSD and Linux. And we're also adding as targets those to run those tests on EC2 and also ARM in the next couple of weeks as well. ARM is pretty interesting to us. I'm not sure how many people are using it, but it's a rising platform, so we want to make sure that RTPproxy is a first-class citizen there. Also on our GitHub account, we have some load generators and memory trackers to keep track of, to basically avoid any memory leaks and so on. And a couple of people are familiar with memory leaks, I think. And we have been too, but that's helped a lot as well. So
Yeah.
yeah.
Just a little bit on that memory thing. It's something I just read for myself. So if somebody needs lightweight, kind of pretty basic, but still working leak tracker, yeah, you can grab it and easily integrate it into your own project. It's basically just a few files, portable, whatever.
Actually, also, I'm not sure if I'm talking about this on a different slide, but we also have another repository on our GitHub page called VoIP tests, and that is a set of integration tests. It's pretty young at the moment, but what it basically does is it grabs the latest OpenSIPs and fires it up and runs some integration tests between RTPProxy and OpenSIPs. The use cases there are very simple at the moment, but we plan to build those out more. So that like the R flag is, we want to exercise that on every build, every commit, and so on, and that will build out more and more as well. Community participation there as well is would be appreciated. Yeah. So the bit about the ecosystem, RTPProxy. I mean, it first targeted SIP Express Router before the 4 cores. And it lives on, like OpenSIPs is well supported, Camelio is also supported. And then we also have our own back-to-back user agents written in Python, which is an open source project as well. So it has strong support there as well. And then also in the broader ecosystem, Wireshark has protocol decoders for the control channels. So if you're debugging your RTPProxy, it's well worth your time to use Wireshark. It makes debugging the actual command protocol much easier. That was written by Peter Lenenkov. Shout out to Peter for writing that decode in Wireshark. Peter actually also ported RTPProxy wholesale to Erlang. So if there's any functional programming, enthusiasts here, go look at that. It's fun stuff.
Okay, so we talked a little bit about RTPProxy history. Now, quite a new thing that we made a few years ago, but we kept it pretty secret from you guys, and we wanted to have a little bit more exposure there. So it started with that original code and original idea of how we could scale up RTPProxy back in the days 2005, 2006. So what we did back then, we just whenever we needed more capacity, we just ran multiple RTPProxy instances, and we had added support into RTPProxy module in OpenSIPs, so it can support multiple RTPProxies. It worked for a while, but unfortunately it was not very scalable solution. You could not really run like 10 of them, probably just few. And also, obviously, since it was inside OpenSIPs module, we cannot do any runtime reconfiguration or changing parameters or anything like that. So there came the idea to build kind of middleman which will sit between your RTPProxies and OpenSIPs, and it basically abstracts all the complexity and presents OpenSIPs with like it would talk into just single RTPProxy instance, just bigger one. So that was the original idea, and some of the design objectives for this module was to make it pretty reconfigurable in the runtime, so you can basically change configuration and reload it without disrupting any traffic. Also, we wanted you to be able to actually monitor and see what's going on, how it works. So there is a support for command socket, so you can connect anytime and check status of your cluster, see how many nodes you have and how loaded they are and stuff like that. Also another thing that we wanted to have is to make this RTP cluster pretty stateless, so you can basically restart it without much interruption. So if your node crashes and restarts, it will basically relearn and find which RTP proxy has which sessions and stuff. So this was kind of basic idea. We worked on this project for a few years, and this is basically some of the practical clusters that we run for one of our customers. So we have about 10 RTPproxy nodes, and those nodes are pretty beefy hardware. It's 15 to 24 cores, pretty latest Intel processors. So yeah, basically this basically depicts the setup. Lines here are obviously not real connections, it's just logical connections. It's all obviously connected through the regular Ethernet.
Yeah, so we have some in-house monitoring tools that are gathering stats from the cluster. It gives aggregate stats for your entire cluster. It tells you how much you're running in terms of traffic, packets per second, and so on, and also on a per node status, so you can focus in on a particular node, see how it's doing. Resolution there is on a per second basis. Yeah, so if you have like a cluster with 60 or 100 RTPproxy nodes, you can ask RTP cluster for its stats, and it'll dump all those stats to you, and you can put it into your own time series database solution, whatever you guys use. As I said, we have our own in-house stuff. We might clean it up and open source it at some point. It needs some love before it sees the light of day. But it goes back to the whole idea of composability. The primitives to get those stats are really simple. So you don't have to use our idea of a monitoring solution. You can plug it into your own existing system.
Yeah, the idea there is pretty simple. RTP cluster abstracts all the complexity. So if you issue some of the command to query this or that counter, it basically sums up all of the available RTP proxy, gives you aggregate stats, so you don't need to know anything about actual config and whatnot. Yeah, this talk was called performance. So let's look at some of the stats that we have from running the setup mentioned on the previous slides. So this is stats collected from actual production system. By design, we have capacity limit of about 40,000 concurrent RTP sessions, and on per node basis, we are limited to about 300 to 400 CPS per signaling node. And most of this limitation comes from the fact that RTP cluster itself is written in Python, so it's basically not speed demon, basically. But it works, and if you need more than that in CPS terms, you can technically run several instances on the same node. Should not be a big problem. You will probably wasting a little bit of memory, but not a huge deal. Yeah, we have about 7 to 10K sessions per signaling node, and here you see we go to about 30,000 active RTP sessions in peak time. We keep it a little bit obviously lower than the designed capacity, so we have some room for traffic spikes, and yeah, those guys usually quite a lot of traffic during eats and stuff, so yeah, it works. Yeah, and basically we can, without changing this design, we can probably scale it up to 2 to 3 times more by just adding more nodes and growing the network that way. Now, if you look at the performance of a single node running RTP cluster, RTP proxy, sorry. This is one of the nodes we have. It's dual socket E5 2620 version 2. 12 cores in total. It has 2 gig ports connected in the LACP configuration, so it basically distributes traffic over those 2 ports. And here you can see some of the CPU usage. I don't know how well you can see the colors on the screen, but basically this lower line here is the user time. So this is basically the actual code inside RTPProxy running. All other CPU usage comes from the system time, which is about this red line, which goes about 40%, and about half of that is are interrupts. So network interrupts take about 25%. So basically, this tells us that we are pretty efficient, and we are not limited by the RTPProxy itself, but rather by the fact that operating system, by the design decision, basically by the fact that we wanted to have everything running in the user land. So I don't think you can see much here, but basically it shows the top running on that node. Here you can see this is RTPProxy actual threads running. So we have 6 instances, each running 2 network threads. So on top this is sending threads, this is receiving threads, and here are interrupts. This next slide. Basically, this interrupt time, it goes up to about each core assigned to interrupts is loaded by about 40%. So basically, overall, we have 12 cores, 6 of them loaded by interrupts by 40%. So we're basically spending about 20% of our CPU budget in interrupts. And then the next biggest user is the sender threads, and we spend about 50%. We have 6 of them, and we spend they use CPUs by 50%. So about 25% of all CPU time goes to the sending, and the rest is receiving and pulling. You don't really see this from this graph, but also from more detailed analysis of RTPProxy, we see that the threads that handle poll and receive, they take about 15% of total CPU time overall, and about a third of that goes to the poll process, poll command, poll system call, and 2/3 of that is actual time doing receive from. So which tells us that we are not going to have much benefit of using more advanced polling method like ePoll or something, because the most we can save is 1/3 of 15% in total, which is like 5%, and So what really limits us on the performance side right now? First of all, lack of real concurrency. Well, not real, but lack of good concurrency in the kernel. Just like RTPProxy started with a single core design, pretty much all operating system in wide use today, they started as single core designs as well. So basically those guys have problems just on the bigger scale, just as we do have scaling up to 16 cores and past that. Another issue here is actual layering in the kernel, which basically has too many layers. Whenever you have to send a packet, it goes through all UDP, IP, all the MAC layer and stuff, and it takes enormous amount of time, CPU time. As you saw from that graphs, we basically using only 15% of all CPU time in userland code. The rest goes to the kernel. And the last but not least, growing complexity of the CPUs as well. So this is not latest, this is Haswell, which is pre-latest CPU from Intel. And as you can see, it's pretty advanced structure inside. So, and this is just one socket. You have two of those in your system, and basically how well operating your operating system, for example, assign CPUs to interrupts affects performance quite a lot, because here you can see the interrupts in physical I/O connected more to those they have affinity to specific cores on the die. They're not connected to all your dies equivalently anymore. So how your operating system does it really affects it. And yeah, it basically varies from vendor to vendor. If you have two socket system now, one vendor might connect your network cards to this socket, another vendor might connect to this socket, and depending on which card you use, is it built-in one or are you using PCIe slot, that also might affect your routing of your I/O basically to one socket or another. But there are some obviously some ways to make it better. We really hope operating system will make some progress in the next little while. Hopefully we'll see better support for concurrency, and so we can run a larger number of threads without incurring those issues. Then there are some work going on making interfaces, implement interfaces which allow your application to talk to the network layer directly. For example, there is a pretty good work on NetMap, and it's available for both Linux and FreeBSD. Yeah, it allows your application to bypass the kernel and put packets directly into network buffer, into network cards buffers. So we basically avoid all the system overhead. All it comes with the price, obviously. You're not having any support from kernel to actually do your networking, so you need to implement all your layers yourself. So you need to do IP, you need to do MAC layer and all this stuff. So maybe it's one of the possibilities that we will have it as an option for one of the future RTPProxy versions, because the gain is pretty good. We can have like 10 times more performance on the same hardware by just doing it.
Yeah, and I mean the OSI model, it's great for generalized computing, but it's when you get specialized with what we're doing with RTPProxy, it gets very slow. There's a lot of bureaucracy in there, and so there's a very strong, there's a very compelling reason for us to specialize and use an interface like NetMap, because we can cut away all that bureaucracy, as Max said, get probably 10 times more throughput on a single machine, and that's a pretty big saving. And with this as well, it's not, it doesn't make RTPProxy become a kernel module. We still live in userland. We still have all the advantages of operating as a non-root user. But it does mean we have to do a bit more, and that's where the specialization comes in. So there's already been some prototyping work on this. It's looking promising, but it's in the future for sure.
Yeah, and another thing that also will need some work before we can go the path is this interface is pretty much single user, so only one application in your system can really use it. So and it doesn't really work with multiple RTPproxies running on the same box. So we'll have to put everything back into a single process in order to actually use it. But yeah, as Jeff said, possible return might be very well worth it.
Is it working like a single thread or single process? You said you can only use it from a single application. Is it single threaded?
No, you can have as many threads as you want,
okay.
but it needs to be single process. So
Okay.
Yeah. So in existing implementation of RTPProxy, we're not constrained by our by the control channel handling, for example, and our PPS and so on, because we're constrained. Our bottleneck is the OSI layer, basically. We've optimized the userland process pretty heavily, and that's not our bottleneck. We're running into limitations in the kernel and the OSI layer. If we remove all that by going directly to netmap, then we have a new bottleneck. And we're refactoring that area before we really follow through the netmap work.
And we hope maybe somebody takes this seriously in the Ausland and works on better interfaces which can take much higher PPS applications, because right now, as we said, it's pretty doesn't look very well. You have a lot of CPU resources and you wasting all it for pretty much nothing. I think that's pretty much it. So yeah.
Any questions?
So is the impetus behind not going towards something like IP forwarding with a kernel module, integrating with IP tables, things like that, just so that you're staying as a user land payment only?
Yeah, we also have other things on our roadmap. We plan on doing transcoding and a bunch of other stuff as well, and doing that in kernel lands. It makes it a bit more difficult. Also, we sacrifice our portability. We support Solaris. Not everyone uses it. We support it. We support Linux and FreeBSD. So staying in user land is compelling for us as well. It keeps us out of a corner.
Sure. Yeah. And just from operational standpoint, we sleep well at night.
Yeah, debugging kernel crashes, it sucks. when someone's,
Yeah, and you see those systems handle quite a lot of conversational traffic, so yeah, you can damage your kernel pretty badly.
Yes, I have a question about TLS. Is it supported with transport layer?
So, like SRTP, secure RTP? Yeah.
Oh, SRTP?
Yeah.
Yeah, there are some discussion going on of implementing it. Basically, we just limited by resources, really.
Yeah, it's something we'd love to do, and we've had some questions about it. It'll probably happen sometime. If there's more demand for it, then it might happen sooner. But yeah.
If you want to jump in and help, we would really glad to.
Yeah, we like pull requests as well.
I was wondering whether the RTP cluster control protocol is compatible with the initial control protocol. I mean, it can be plugged right now in OpenSIPs.
It's totally pluggable. It basically doesn't have its own protocol. It uses RTPProxy protocol.
Oh, okay.
And on control side, it has two sockets. It's basically one that you use to send commands, and another one for administration, which basically allows you to connect and change parameters and
and the command channel for RTPProxy has remained backward compatible. The middleware here, which is RTP cluster, is just it uses the exact same
Just
command
an
channel.
extra layer that uses basically proxies or proxies
exactly.
components.
Yeah. Any more questions? Yep.
I have another question about steps. You were saying, is it integrated somehow with some databases? So There has to be something else that pick up the stat.
Yeah, so the primitives are there to, you can either pull the RTP command socket for those stats, or you can get it to write it to a log, and you can use like a log collector. But so we've given you the primitives, and we haven't provided anything beyond that. But it's very simple, so you should be able to get it into your own system quite easily. The system that, if anyone ends up writing like a Flume collector or whatever, it would be cool to get that into a contrib directory in the repo so everybody else can use it. As we come across those things or write them ourselves as well, we'll put them into GitHub. It hasn't been a priority for us, but we'll definitely make it easier. Point being, the primitives over there, they're super simple, so it shouldn't be too difficult.
Yeah. All counters, I think, are documented.
Yeah.
You can check the website.
Yeah.
And yeah, we have this monitoring script, and it's really simple right now. Basically, what it does, it goes to specified list of sockets, pulls the stats, sums them up, and invokes a RD tool to put them down into the disk. So yeah, basically, it just needs a little bit of cleanup. We might just revisit someday.
Yeah.
So not kind of a big deal for us.
Yeah. So yeah, come talk to us. We're here. Yeah.
How do you guys handle like various types of attacks, like injection attacks? You deal with it, or you just proxy in some other stuff?
Yeah. So we haven't had much of a problem with it. Like we always everybody gets junk traffic on various ports. But the command channel, like in our deployments, is always like firewalled off, private, so we don't have any issues in the command channel side of things. And when a session gets set up, it's very explicit, sender, like IP address, port. So if it gets anything from anybody that isn't, doesn't match the hash table that's in there, it's just discard it.
Yeah, another thing that we employ like a port randomization. So we allocate ports randomly, and it should be pretty difficult to guess what the next port might be. On top of that, I think in the newest code we also track, also actually parse RTP packets and track SSRC ID. So technically, you can, with little work, you can harden it up. So it doesn't.
We have problems with see people just keep spamming everywhere. So it's not that they know which port, it's just that they keep spamming everything. Eventually they'll hit something.
Oh, yeah.
And is it pretty specific targeted attacks, or is it just random junky traffic?
It's random junk traffic.
Okay. Yeah, generally what we see in production is that we just drop it, and it doesn't bother us.
If you're on private network, yeah.
No, well, I mean, the RTP proxies are that actually send and receive your media are public, and they have to be because but each port is strongly tied to a IP port address. So if you're getting some random like IP address spewing garbage, you're just like I don't know, but this is garbage. So
yeah, it should be discovered.
Do you have a mode where you can actually have a lot of RTP or whatever certain amounts of periods latch on to one of the IPs just because you can't really trust it to begin with?
Yeah. It basically, there is a little bit of that. I think we have some kind of window parameter inside RTPProxy which defines number of seconds you're allowed to change this IP after your initial packet is latched. So there are at least some of the protection for that. Obviously, if you find a better way to do it, just let us know. We will implement it.
So RTP cluster is available on our GitHub. It was hiding in a subdirectory of a different repos, so it's got its own top level project now. It's just put there, so we're still giving it a bit of love, and it needs a love. But go look at it. If you have any issues, open tickets on GitHub, ask questions, or come see us. We're here. Yeah, big thank you to Bogdan, Alex, the OpenSIPs team for organizing this. It's really cool that you guys listened to us for 45 minutes. Thanks as well to the sponsors, 46 Labs, RateTel, and SIDPulse. Yeah, it's good to be here. This was the first time us doing this talk, so yeah, it's been good.
Yeah.